Hello again. Well, let's continue talking about discounting, and we're going to apply it to Prisoner's Dilemma. So consider this Prisoner's Dilemma game where you can be either nice or mean. And I'm going to look at most Prisoner's Dilemma games. I'm going to label the strategies as nice or mean, where obviously being nice means doing something that the other person would prefer. So first of all, the reason this is a Prisoner's Dilemma is that being mean is a dominant strategy. You can see this person is nice, you'd rather be mean, and if they're mean, you'd rather be mean, and the game is completely symmetrical. Most of these games we're going to be playing with Prisoner's Dilemma now, they'll be symmetrical games, so it doesn't matter if you're player 1 or player 2. So you can see mean is a dominant strategy, but of course if everyone's mean, that's worse than if everyone's nice. So this is a Prisoner's Dilemma game. And if you play the game just once, you would expect everyone to be mean and to end up here. Now, what if you were to play this game 3 times? So if you were to play the game 3 times, and what would your payoff be? Imagine you played the game 3 times, and you end up with this bad outcome. So every time both people play mean, and you end up getting 2 each period. Let's use discounting and see what would happen. So if we have a discount rate of 1/2, which just means you value money that you're promised next period half as much as if you were promised at this period. So that means someone giving you $10 today is just as good as them giving you an absolute promise of giving you $20 a period from now or $40 2 periods from now. So if you were to play this game and you figured, well, we'll play it 3 times, and for some reason you think you'd end up here 3 times, your payoff with discounting would be 2 times delta to the 0 plus 2 times delta to the 1 plus 2 times delta to the 2. Remember, now is always defined as period 0. So if you play a game 3 periods, first you get it in delta 0, then delta 1, then delta 2. And if I've told you delta is 1/2, we can just put in the 1/2 for the delta, as you see here. And then we can work this out. 2 times 1, 2 times 1/2, 2 times 1/4. And this just represents the 2 you get right now is just worth 2 to you. The discounted present value of getting 2 a period from now is 2 times 1/2. If delta is 1/2, it's half as much. And then if it's 2 periods from now, you do the half twice, so it's 1/4, and that comes out to be 3.5. So if you anticipated, I think we're going to play this game, and I think I'm going to end up here 3 times. What's the discounted present value of ending up here 3 times? If the discount rate is 1/2, the discounted present value of ending up here 3 times is going to be 3.5. And hopefully that makes sense, because you'll say, I'll get 2 3 times. I'll get 2 right away. The discounted present value of getting something right away is just that something, right? $2 today is worth $2 today. But then what's $2 getting next period worth today? Because the discounted present value is always saying what's the present value of future wealth. Well, if delta's 1/2, the value of getting $2 1 period from now is 1. And then what's the value of getting $2 2 periods from now? What's the discounted present value of getting $2 2 periods from now? Well, if delta is 1/2, it's 1/2 times 1/2 or 1/4. So you get 2 plus 1 plus 1/4, and that's, of course, 3.5. Now, is it plausible that if you played this game 3 times and everyone was super rational, you'd end up here 3 times? So if this were class, I would have you play this game 3 times with, your neighbor, and we would tell you, I'd say, discount rate is 1/2, what do you get? And a few of you, based on past experience, would end up here, but not all of you. So think about this now. Maybe pause the video. 2 rational people, it's common knowledge that they're rational, play this game 3 times. Delta is 1/2. Their goal is to maximize the discounted present value, their payoff. So when deciding their strategy, they try to maximize the discounted present value of their payoff. Do you think they'd end up here 3 times? Again, pause the video, give some thought to this, please. Or, maybe if you have a relative around, you could explain the rules and play the game. If you don't want to explain discounting, that would be fine. You could just play the game 3 times, ignore the discounting, and say your goal is just to maximize your payoff. So that could be a family game. So what do you think would happen? Well, if the people are rational, they really should end up here 3 times. And we get this by solving backwards. Remember, solving backwards often is the best way of solving these games. So let's imagine that you're thinking of what strategy to do, right? And you haven't started the game yet. You might think to yourself, yeah, I'm always better off being mean in any one period, but maybe I should be nice initially to get the other person to be nice to me in the future, right? Maybe in the initial round 0, you're thinking, I should be nice to get them to be nice to me in future rounds. But that doesn't work if you think about solving backwards. Let's go to the final period. Okay, you're going to have one final move. Remember, it's a simultaneous move game, so you're going to pick nice or mean, the other person will pick nice or mean, and the game will be over. What should you do in the final period? Well, in the final period, you should definitely be mean, right? There's no reason not to be mean if you're playing this game for the last time. And think about it. It sounds reasonable that you should play nice occasionally in order to get the other person to be nice to you in the future. That sounds plausible, but that can't possibly be true in the final period. In the final period of this game, there's no value in being nice to the other person, because the only reason you'd consider being nice to them is so they'll be nice to you in the future. You're being nice to someone in the final period can't possibly cause them to be nice to you in the future, because there's no period after this one, and it's a simultaneous move game. So whatever you do this period can't influence what they're going to do this period. So in the final period, you definitely want to be mean, and of course you expect the other person to be mean as well. What about the period second to last? Well, again, in the second to last period, you're always better off that period being mean, because mean is a dominant strategy. You'll get a higher payoff. Maybe it's worth it to be nice to them if it'll cause them to be nice to you in the future. But no, because in the future, in the last period, they're going to be mean. So no matter what, if the other person's rational, she's going to be mean to you in the final period. So in the second to final period, what's the point of being nice to her if you know she's going to be mean to you in the final period? And then, of course, you probably figured out this means in the initial period, you might as well be mean, right? In a 3-period game, period 0, 1, and 2, she's going to be mean to you in period 2, the last period, because there's no other period. Well, that means she's also going to be mean to you in period 1, and so what's the point of not being mean in the initial period? This is a very paradoxical result, but it's pretty solid if at least it's common knowledge that people are rational. If you play a prisoner's dilemma game a finite known number of times, every single round, everyone should always be mean. And this is really counterintuitive. Many of you thinking, he's probably making a mistake or something's weird's going on, but it's not. Let me go over again what's happening. So you're playing a prisoner's dilemma game, finite number of times, and everyone knows how many times you're playing. You're playing it 1,000, say. Everyone knows you're playing it 1,000 times. What will happen? Again, it's common knowledge, everyone's rational. Clearly in the last round, you're going to be mean. The only reason to ever be nice to someone in a repeated prisoner's dilemma game is that it might convince the other person to be nice to you, right? I'm always better off in the current round being mean, but maybe it's worth being nice to you if I think it'll cause you to be nice to me in the future. I can't cause you to be nice this round because you move at the same time I do. So when you move, you don't know what I'm going to do. So I'll only consider being nice to you in a repeated prisoner's dilemma game if I think it will cause you to be nice to me in the future. But in the last round, there is no future. Definitely going to be mean. What about the second to last round? Well, in the second to last round, I should think you're going to be mean to me in the last round no matter what. So there's no point in my being nice to you in the second to last round. And then, of course, the third to last round. Well, look, in the next 2 rounds, you're going to be mean to me. So what's the point of being nice to you? And we go all the way back to the first round, which again is in round 0. That's very weird, very counterintuitive. But again, the finitely repeated prisoner's dilemma game, where it's common knowledge everyone is rational, everyone is always mean. You're stuck in the prisoner's dilemma and you can never get out of it. Well, there are 2 ways. The first way, and this is relevant to this class, is that if this is a real life situation, you figure out a way of changing the payoffs, right? I mean, I've made this game nice and mean, and I've assigned payoffs. Change the game, make a bribe to the other person, come up with another strategy. So I can give you a prisoner's dilemma game in class, and in the class you can't say, well, I'm just going to change the payoff so I can have it easier, right? That's not allowed. That's like on a math test saying, darn, if this wasn't x squared, but just x, it'd be so much easier to solve. I'm just going to make it x. All right, you're not supposed to do that in an exam. But in real life, darn, I can't solve the problem. But if I make it easier, that's a good thing. That's winning. So if you find yourself in a repeated prisoner's dilemma game, try to change the game. Your coworker and you are in a situation where you're both trying to do a little work and cheat the other person. Maybe change the rules. Maybe say, hey, let's talk to our boss and agree to have the assignments or have the reward this way. You might be able to get out of it. So, in class, I've given you the game, you're stuck with it. In real life, you're not. But another loophole is, remember I said, finitely repeated. Everyone knows when the last period is. What if that's not true? What if you're playing a prisoner's dilemma game an infinite number of times? Then there's no last period. Or what if you don't know how many? What if you don't know when the last period is, and there'll never be a time in which this is the last period? You're going to play it with someone else for as long as you live, but you don't really know, like, well, on this day is the last day. I can't, if I'm alive then, I know I can't be alive the day after that. That doesn't happen. So the reason that you're stuck in this situation, you're stuck in the prisoner's dilemma with rational people if you're playing it a finite known number of times, is because we can start at the last period and work backwards. But what if there is no known last period? Which can happen if you don't know when it will end, or it goes on forever. People don't live forever, but corporations can. Then you might be able to get out of the repeated prisoner's dilemma. And we're going to be examining that situation if you play a prisoner's dilemma game an infinite number of times. Now, in order to play a prisoner's dilemma game an infinite number of times, we're going to need to talk about how discounting works if you have an infinite number of these. I mean, what does it mean? And that'll be the next video. We'll talk about discounting when you have an infinite number of things. Thanks, and goodbye.